So today we're going to look at how do similar polygons work with proportions. Similar figures are always proportional to each other. Doesn't matter whether it's a quadrilateral, a triangle, a pentagon. If they're similar, and we'll define what similar means in a minute, then they're also proportional. So 7-2, it's very exciting. We are going to explore similar polygons. So in order to do that, we better define what a similar polygon is. So similar figures occur when figures have the same shape but are different sizes. This occurs with a dilation. So a dilation is one of your transformations that will blow something up bigger, but a dilation also means in mathematics that we can shrink something down and make it smaller. So here's your actual definition of similar figures. Or we'll say similar polygons. That's a Y. Two polygons are similar if and only if their corresponding angles are congruent and the measures of their corresponding sides are proportional. You have to apply two tests to determine if two figures are similar. That's assuming that they haven't told you that they're similar. So if you're trying to determine if two figures are similar, two tests have to be applied. Test number one, their corresponding angles have to be congruent. All corresponding angles, not just two of them, not just three of them, but every corresponding angle. And what does corresponding mean? Same place, right? So when they draw these figures, they may not be oriented the same. So what I tend to do is I will cross one figure out and redraw it so it's turned exactly the same way as another figure. So I can look to see exactly where the angles are. Arc marks, you don't necessarily have to know the exact degree measure of the angles, but arc marks could tell you that corresponding angles are congruent. So single arc marks mean those are congruent. Double arc marks mean that those corresponding angles are congruent, that type of thing. And then the second test is that the measures of all corresponding sides are proportional. So you would set up each of the corresponding sides into a ratio and reduce that ratio. If they're all the same fraction, then they're all proportional. But you can't have even one set of sides being a different ratio than the other set. And so because we're talking about a dilation, dilations occur when we have a scale factor. So a scale factor would be the ratio of the lengths of two corresponding sides. I guess we should add in here of 2 similar polygons. And you might want to add in here, in case you didn't know or didn't realize, that a dilation reduces or enlarges a figure. All right, so let's see how that works. So let's look at example 1. And there's oftentimes more than one way to approach a problem. Trapezoid, PQRS, is similar to trapezoid UTWV. Find the value of x. And again, even though some of these you can do by logic reasoning, I want you to get in the habit of setting up a proportion so that when the sides become more complicated looking, in other words, an expression rather than just a number, that you understand how to set up that equation to solve. So here's our 2 trapezoids. So the minute that they've told you that the 2 trapezoids are similar, the 2 things above here, these 2 things right here, apply. All of their corresponding angles are congruent and all of their corresponding sides are proportional. What's nice about trapezoids is they have a long base and a short base. So other than maybe perhaps having to reflect something, I can pretty much be assured that these 2 are corresponding angles, those are corresponding angles, those are corresponding, and those are corresponding. The only difference might be is if I had to flip one to make it the other one. But for this purpose, it won't matter because I'm just going to give you side lengths. So QR is 14, QP is 6, and RS is 6. And PS is 8. So you know everything on the smaller trapezoid. What kind of trapezoid is the smaller trapezoid? It's isosceles. How do you know? The legs are congruent, right? So knowing that, aren't the base angles here congruent and the base angles here congruent? So this had better be an isosceles trapezoid also because that's the only way they could be similar. So this is 35 between W and T. Between U and V is 20. And then if I make WVX then TU would have to be X as well. So you can look for a scale factor between the two. The problem with this one is there's nothing that I can multiply 14 by to get 35, right? Oftentimes we could do that. So if I could multiply 14 by 2, I would get 28. So if that were 28, my scale factor would be 2. Or it could be 1/2, depending upon what direction I'm looking at. So my scale factor from here to here would be 2. From here to here would be 1/2. But I didn't get 28, did I? And same thing here. I can't multiply 8 by anything to get 20. So proportion would be handy. You choose one corresponding side here and one corresponding side here that you have both numbers to. So in other words, I wouldn't want to choose 6 and X because I don't have both numbers to, well, I guess it'd be this 6 and this X. I don't have both numbers to those. So you got a choice. What could you choose? I could choose 14 and 35 or 8 and 20, right? I could choose either one of those two to be my full ratio. It doesn't matter. So we could choose 14 over 35. Could you do 35 over 14? Sure you could. You absolutely could. So, and for my purposes, I am going from small to big, right? So I've got small over big. It's important for you to write that down so that you remember what goes up top and what goes on the bottom. And so then equals, if I'm trying to find X, it's got to be the 6 and the X, right? Well, which one goes up top, the 6 or the X? The 6, because it's small. The X is big. You solve that proportion. If I were you, I would reduce the 14 and the 35 first. So share your answer with those around you. What'd you get? 15. And here's how you can check. I chose to take 14 over 35 and I reduced that to 2 over 5. My scale factor is equal to 2 over 5 because I'm doing small to big. So then take your X and put it in here. So now take 6 over 15 and compare that scale factor, reduce it. What goes into both 6 and 15? 3. So 3 goes into 6 twice and 3 goes into 15 5 times. Do they match? Yeah. So I must have a good answer. So that's how you can check your answer. So you're going to have all kinds of different sizes. Now, what if I'd given you angle information here? Would you have set up a proportion? What do you know about congruent angles? What if I had said, this one is, we'll make it 120 degrees, and this one is 3x. What would you have done to these angles here? Would you have set up a proportion? What do you know about corresponding angles in similar figures? They're equal. So if I had given you that, you would have 120 equals 3x. You'd set those equal to each other. I guess I should put a y, right? Because it's different than our x. So wouldn't I say y is equal to what? 40. Or not degrees, just 40, right? So there is a difference between whether you're looking at corresponding angles versus corresponding sides. Corresponding sides are proportional, you'll set up a proportion. Corresponding angles are congruent, you'll set up an equality statement, no fraction. Okay? So look at this next one. This next one is more useful to you in real life because it's something that perhaps you might have come across or you will come across, one of the two. So example 2. Of course, I'm one to talk. My family laughs at me. I am not allowed to be the navigator of my family. I get lost in a paper sack. I can't even find my way out of it. I don't know where north, south, east, or west is if I'm in a city. I got lost in San Francisco one year, lost my brother's rental car. Did I tell you that? Yeah, because I couldn't figure out where the parking garage was that I parked the car. And it's shocking to teach geometry, isn't it? All right, so here we go. How long would it take to drive the north to south dimension of Delaware? I've never been in Delaware. It measures 3.3 centimeters on the map. And you would average 50 miles per hour. So that's typical of something I would do. Look at the map and go, oh, that's only a little over 3 centimeters. It won't take us very long. It's so tiny on the map, right? What's important to note when you're looking at a map? Does every map have the same scale? No. So what's one distance on one map is a different distance on another map. So something that might be of interest to you would be the scale on the map. So the scale on the map would be 2 centimeters is exactly equal to 50 miles. Which is your map scale. Alright, so this is a word problem. Please, in your word problems tonight, set up your 4-step plan. Don't forget. What is it that we don't know? Yeah, so we're going to let, and you can, bless you, you can let it be x or t, whatever you want it to be. So I'm going to let x equal the time to drive north-south, bless you, dimension of Delaware. That's what we're trying to find. Now, yesterday, didn't we deal with dollars and Spanish pesetas? Right? And didn't we use that as a ratio? This is no different than $1 equaling so many Spanish pesetas. This 2 centimeters is exactly equal to 50 miles. They're equal measurements. So you can set up a ratio of 2 centimeters over 50 miles or 50 miles over 2 centimeters. It doesn't matter. You decide what you want to go up top and what you want to go on the bottom. So what would you like to go up top, centimeters or miles? Centimeters. Does it really matter? No. But once you make a decision, it does matter. Every ratio in your proportion better be centimeters over miles. And we will ignore the centimeters and the miles because you should know, based upon where your variable is, whether you're getting an answer in miles or centimeters. So do we have a full ratio of centimeters to miles? Do we? Do we have a full ratio of centimeters to miles? Your map scale, isn't that your ratio? It's just written in equality format. So can't I write that as 2 over 50? There's my left side of my proportion. So on the right side, I should have a partial information. Now, what do I put in this side? Do I put 3.3 centimeters or do I put 50 miles in there? Which one is the one that's applicable to our equation to solve? Yeah, because this is what? What does the 50 miles per hour represent? Isn't that a rate? Okay. Once I know exactly how far I'm driving, then I can use that rate. So we're going to have to do a couple of different things here. So what goes up top here? The 3.3. So what am I going to put here? S. Because that's our That's not our time, that's our miles. What's wrong about this? Is that our time? So here, what do I have to know before I can find my time? This is my distance. So I have to make a little adjustment, don't I? Because what I put here is not time, it's my distance, right? I have to know that before I can find my time. So now, can't I cross multiply and solve? Would a calculator perhaps be handy here? It would be. And if you're going to use a calculator, then you really wouldn't need to reduce, but you could reduce the 2 and the 50, but I'm going to help you out with your calculator. So cross multiply. 2 times x is 2x. 50 times 3.3 is going to give you 165. Divide that by 2. What do you get? Yeah, 2 goes into 16 8 times. 2 goes into 5. How many times? 2. 2 times 2 is 4. How many is left over? 1 out of 2. So 82 and a half or 82.5. And what is x? What unit of measure? It's in the bottom, so isn't it miles? It's important to write that down so you don't forget. So now I know that the north-south dimension of Delaware is 82 and a half miles. Are you aware of what Delaware looks like on the map? Because that doesn't seem very big, does it? It's about that far to Flagstaff, give or take a few miles. Is Delaware a very big state? No. It's a super teeny weeny tiny state. So that is fairly accurate. All right, so that doesn't answer the question, does it? So what do I have to do? Right, don't we have this formula that you've been using for years? Rate times time equals distance. Which of those 3 am I trying to find? Time. So how do you solve that equation for time? Divide by rate, right? And so if I want to find my time that it takes to go the 82 and a half miles, I need to take my distance of 82 and a half miles and divide it by my rate, which is 50 miles per hour. So time is equal to my distance of 82, and I'm going to make this 0.5 because we're going to use our handy dandy calculator, and divide it by 50. Now this is miles, and this is miles per hour. What's going to happen for miles? They're going to cancel, and you're going to end up with a time in hours. So if I divide that out on my calculator, I get t is equal to 1.65 hours. Do you know how I would convert that to hours and minutes? How would I convert the 0.65 to minutes? How many minutes are in an hour? 60. So if I wanted to find out how many minutes, I would take 60 minutes and I would multiply it by 0.65 because that's 65% of the total, right? And in this case, I would get 39 minutes. So this is either your answer, or you could have 1 hour and 39 minutes. It depends on what they're asking for. If they ask for the answer in hours and minutes, then you have to convert that decimal portion into the minutes. Just take it and multiply it to 60. So write your therefore statement. Therefore, it would take 1 hour and 39 minutes to drive, the north to south dimension of Delaware. So here's the last thing I want to show you. I don't want you to write this down. I just want you to look at it. And if you want to get the notes, you can just print them, this part from offline. So we've done a lot of things in the coordinate grid, right? So let's just say that I gave you this. I gave you vertices and it's a square, and you already know about a square. Stop wrestling and just listen. Don't pack up. All right. So you already know about a square that's got 4 right angles and 4 congruent sides. It says if the coordinates of each vertex are multiplied by 3, that's the scale factor. That means we're dilating something. Okay? So if I multiply each of these by 3, 0 times 3, 0 times 3 is still 0, 0. So that coordinate point didn't change. But what's 5 times 3? 15. And 0 times 3 is 0. So this point becomes 15, 0. And so that's why I'm out here at 15, 0. Don't pack up. I'm not going to ask again. Stop it. It's loud, noisy, and you're not listening. Then this one got multiplied by 3, so it became 0, 15. And this one got multiplied by 3, and it became 15, 15. So there's the 15, 15. Whenever you dilate something, its new ordered pair is the same letter. So like these are the same letter, but remember you got a prime. We did that in Algebra 1-2 last year. So here's my original, here's my dilated figure. If it's dilated, it should be similar. So the question is asking you, will the new figure be similar to the original? Well, I already know that I have 4 right angles because I have vertical and horizontal lines, so I don't have to test that in this particular coordinate system. But then notice what I'm doing. I'm setting up each of the corresponding sides, original to dilated. So like DF to DF prime. So this side is to this side. And because I have perfectly vertical and horizontal lines, I did not have to use a distance formula. I could just count squares. If they're not perfectly horizontal or vertical, you have to use a distance formula. And then you have to compare their ratios. Don't all of these reduce to 1/3? And in this case, they were all 5/15. Since they're all the same, the figures are similar. So if you have a problem like that, you're going to have to make the comparison. And you're going to have to apply the 2 tests. Do I have corresponding congruent angles? And do I have corresponding proportional sides?